Friday, Baylor College of Medicine and friends of Baylor. We are very lucky today to have our newest center director, Dr. Joe Rogers. Joe Rogers. You're going to be Joe Rogan soon.
Sure.
Dr. Joe Rogers, who was the CEO of Texas Heart Institute and is now the center director of the Texas Heart Institute at Baylor College of Medicine. And we are so excited to have that whole group of folks come in. And actually, Dr. Rogers took me on a tour of of the Heart Institute the other day, and I got to meet some of the really terrific scientists who are doing interesting work in how extracellular matrix impacts inflammatory responses of the heart, and how you can transform certain cells into functioning cardiac myocytes to replace scar tissue and regeneration, all kinds of great stuff. But I think, correct me if I'm wrong, but please not too much. One of the things that's really known for the Texas Heart Institute was the device development. I mean, I think it led the world in devices used in cardiac disease. And actually, in the 60s and 70s, DeBakey and Cooley were the dominant players.
It was the place.
It was the place
to go for either research or clinical care in artificial heart technology.
Yeah, it's so cool because the history of that is
It's
amazing.
a wonderful legacy. Every device that's on the market today has either been developed or iterated in our laboratories, which is really amazing.
It is cool, and I mean, actually, before the one we're going to talk about today, but like the Jarvik heart and all that, which was developed. Where was that developed? In Utah? Where was that?
Yeah,
in Utah.
In Utah.
But one of the first people to put it in, right, was Bud Frazier.
That's right.
So tell us a little bit about that and how we were involved with the early development.
So, Dr. DeBakey actually was out ahead of this and was thinking about left ventricular assist devices way ahead of everybody else. He didn't actually think that the total artificial heart was going to be the dominant device for people who had heart failure. And in fact, he's probably right, because it's usually the left ventricle that fails. But there is a cohort of people that do better with total artificial heart technology. Dr. DeBakey had recruited Domingo Leota from Argentina to work in his lab. And Leota had a prototype of a total artificial heart. But Dr. DeBakey thought that the LVAD was the way to go. And so that's how Cooley and Leota started to work together.
I remember Barney Clark,
yeah.
right? And I remember being on national news, and
he'd had a bunch of strokes, and it reminds me a lot of the xenotransplant work that's going on now. It's people who really don't have an option for therapy, and they're giving of themselves in clinical research to allow us to learn.
So you could, I think it'd be reasonable to say that the early total hearts were so weird. Problematic, it required so much, and the patients were so bad off that really it was the LVAD technology, the left ventricular assist devices, that really sort of transitioned the field, don't you think?
Oh, completely. And it's those devices have absolutely dominated the field of advanced heart failure. And one of the other interesting backstories to LVAD therapy is the transition from making artificial heart technologies that pulsated to continuous flow devices. And the person that drove that entire conversation was Bud Frazier.
So, this was something I didn't know until I started talking to you and those guys. That the continuous flow, which made total sense to me, sounds right, but it's not very good for the body, because right?
So this is, and we still debate this. Does the body actually need pulsatile blood flow? Because as you know, at the capillary level, the smallest blood vessels, blood flow is continuous. And that's where all the action of the circulation occurs. So it's a really interesting debate, which is somewhat moot now, because we've demonstrated that people don't need a normal pulse pressure, or a blood pressure that's like 120 over 80.
But do they need some pulse, or?
We don't know yet.
No, we don't know. So I think the issue is really, because of the larger vessels, right, that do, and they're remodeling all the time from the stress.
They are, and there's certainly some adverse events that occur because of continuous flow that you didn't see in pulsatile devices, but we keep iterating and re-engineering these devices, and they're getting better, and we're seeing fewer and fewer complications.
Well, I'm happy to volunteer for the non-pulsatile flow, Because what
They're
I don't
small.
like is getting all nervous.
The thing about going to these continuous flow devices is that they're smaller and we can run them electrically much more easily. So they have fewer failure modes. When you put a pulsatile device in the circulation, you have to have valves in it to keep the blood from going backwards.
That's right.
This is moving blood forward in a continuous way.
That makes sense. To me, it's really fascinating. And so tell me, so most of the devices going in with end-stage heart failure are LVADs, and is it mostly, is it permanent or is it just a bridge to transplant?
Both. So originally approved as a way to get people by until they could be transplanted. And then there was this recognition that there's an even larger patient population who will never be candidates for transplant. And that's really the group that we've focused on.
So I'm really excited because I asked you specifically to bring the latest version of a completely implantable heart. And can you tell me about that? How was that developed? And
Sure.
Because it sounds like it took some of the LVAD principles. And
Exactly. So I think that's part of the story of the Bivacor total artificial heart. Bud Frazier and Billy Cohn had been very interested in trying to use these continuous flow devices to create a pump that supported both the right and the left side of the heart. And we're basically configuring two LVADs, to pump in series. And so really it was Billy and Bud that attracted Daniel Timms, a young biomedical engineer from Australia, to begin developing his device at THI and at Baylor. And that work occurred over about a decade, interrupted a bit by COVID.
wasn't everything interrupted by COVID?
Yeah, exactly.
Yeah.
So that whole story, the whole evolution of that device really occurred in Houston at our organization.
And with that, first it went into large animals and
Right. So first in the lab, just pumping water in mock loop circulations. Then we did a series of calves. And the reason we used that animal model is because the chest cavity size is about the same as an adult male.
I see.
So we probably did 50 calves, over the span of those 10 years, and got it to the point where we were ready to do first in human trials. So the story I really like is that we went from an idea
right.
to first in human in our organization.
And that it was built on the principles that were developed in the 90s and 2000s with LVADs. It really is very cool. So, who was the first person to get it? Where did it happen? And how many are going to be done? And are they going to be just used as bridges? Because it obviously seems eventually you'd want it to be a permanent solution.
Correct. So the first person was implanted last summer, the day after Hurricane Beryl.
Perfect.
It was scheduled on that day. We
Welcome to Houston.
We canceled it that day. So the first one was done the day after Hurricane Beryl here at Baylor St. Luke's. The way this worked was the FDA allocated 5 patients who were going to be bridged to transplant in the U.S., which is another neat part of the story, that we're doing first in human in the United States as opposed to some other country. So we put 2 of those first 5 in, and then one was done at Duke, one was done at Christ Hospital in Cincinnati, and one was done in Phoenix. Okay. All of those patients successfully bridged to transplant. The longest implant was about a month.
And how did they do?
They've all done beautifully.
And thanks for throwing in that little thing for my wife at Duke. We allocated one heart for.
Well,
Anyway,
then they've done 3 in Australia.
Okay.
And the next iteration of the device that we'll take a look at in just a second has a sort of a fortified drive line. So the first 5 people in the United States had to stay in the hospital until they were transplanted. This next iteration, people will be able to go home. And that's what the first Australian was home for 100 days on a total artificial heart, right? Which was really pretty amazing.
What's the energy source? How does it keep going?
Runs on electricity.
And how long does the battery last?
Yeah, so the batteries, so we give people several sets, but the batteries will last 6 or 8 hours.
And then you can do the rest?
Cannot. So there's a drive line so that we plug into a small computer that people wear on their belt, and that computer runs on battery power. So during the day, people are ambulatory, can do whatever they want. At night, they plug themselves into the wall and recharge their batteries.
Me too.
Exactly.
Okay. Well, that is really very close to having what everyone hoped for, which is
So once we get through the bridge to transplant trials, we'll move on to patients who don't have transplant as an option. And the FDA has basically said, look, there's no backup system if this fails. We want to have a confidence that this device works the way you think it does.
Right.
In the lab, we've had these devices pumping for more than 4 years without failure.
Wow. And why is, I think this is really interesting. Why is this one so free of the failures that the valve and vacuum?
Right. So there's two things that are very novel about this particular device. Because it's a continuous flow pump, it doesn't need valves because there's no way that blood is going to flow backwards as long as there's power supplied to the pump and the rotor keeps spinning. The second thing is that all of the old total artificial hearts had blood sacs.
Yeah.
And our hearts beat tens of millions of times a year. There's no biomaterial that was ever invented that's been designed to flex that many times. There's no touch points inside this device. The rotor is held perfectly centered in between two electromagnets, so there's nothing to wear.
There's no friction.
So there are no blood sacs, there are no valves. So we really think this is a durable solution to people who need total artificial
It's a
heart.
lot like the LVADs, the little LVADs. So
yeah.
it's very cool. Anyway, I asked Dr. Rogers to bring one here, and luckily Amazon just delivered this. And they had same day delivery at only $2.95 extra, and we're lucky.
It seemed worth it.
It seemed worth it. Show us how it works and how it's implanted.
Yeah, so these are obviously not put in robotically. This is the big sternotomy cut. These are the two atrial sewing cups. So we basically amputate the bottom part of the heart and we sew these to the remaining atrial tissue. And then these are your great vessels, your aorta and your pulmonary arteries. So the connections are pretty easy. And then this is the electrical cord. We just tunnel this underneath the skin and it comes out your side and that's what plugs into the computer. So
eventually, I would bet if you had, the power is then in here.
the power gets to, this is the power that gets to the two electromagnets, one on each side that spins the
So
rotor.
eventually, if we had the right energy sources, it could be without even the tube. And
So that's the end game for all of these devices, right? Is to get the battery technology caught up with this, because what we need is a capacitor that can be implanted under the skin that holds enough energy to run the pump for several hours.
it's not much bigger than a normal heart.
That's
It's
right.
really kind of amazing. So this is one of the really great technologies that has been developed by the folks at Texas Heart with the inventor in Australia. And we're excited that this is going to be part of the program that's going forward. And Joe, thank you so much. This is one of the cool things. I was so excited about talking about this. Thank you for joining us today. Really appreciate it. You're doing great work. Thank you.
Absolutely, Paul. Thanks for having us.
All right, man.
Thank you.
Okay, I want to end today with a couple of shout outs. First of all, the National Endowment for the Humanities has awarded a $500,000 grant to Baylor and Rice University to establish the Center for Humanities-Based Health AI Innovation. And this is intended to embed humanities research in the development of trustworthy health AI technologies. And congratulations to Dr. Vasiliki Rahimzadeh, the assistant professor at Baylor in the Center of Medical Ethics and Health Policy, and Dr. Kristen Osler, director of the Medical Humanities Research Institute at Rice, will be co-directors of this new center. This sounds like a very cool kind of thing, looking at AI in use in patient care. Also, a paper was recently published in the American Academy of Pediatrics Journal about Baylor's 4-year residency in pediatrics and global child health. Although there are other pediatric programs that have global health tracks within their years of training, Baylor is the only one that provides an additional 12-month clinical experience in a resource-limited setting. I have been to all of those centers, and it is really remarkable the kinds of work we are doing in resource-limited countries, particularly in sub-Saharan Africa. And I'm very proud of this program, and congratulations to Dr. Stephanie Martin, Dr. Heather Hack, and their team on their outstanding work. And today is the final day, Janet, listen up, the final day to provide feedback on the 2025 Central Services Survey, something we're all looking forward. I can hardly wait to get my Central Services Survey. This is about information technology, facility, and most importantly, and what we care most about, food services. So if you have any of your complaints about the food services, this is your opportunity. And finally, my second grandchild was born yesterday, or this week, Connor Hudson Klotman. Congratulations to my son and daughter-in-law and grandma. Anyway, great to see you. Can't wait to see you next week. Thank you, Dr. Rogers, and I hope that you have a wonderful weekend. See you next week.
Congratulations on your grandkid.
Yes, I got a grandkid.
You got a picture?
30, I do.